Hello, my name's CalebOrtega. I am finishing up my master's in GIST, and my presentation is going to be about the effect of solar and agrivoltaic arrays on local temperatures. So, some introduction before we get started. I just want to paint kind of a broad energy landscape uh, setting. So, according to the International Energy Association, global solar energy capacity is expected to increase by 2,400 gigawatts. And why this is important is that this energy increase represents the total amount of installed power of China today. And in the United States alone, the solar industry is expected to triple in size. All of this is to paint a picture of the growing market of solar, and it is not going anywhere. It is a dominant energy source in the United States. Current projections state that by 2028, the industry will add approximately another 236 gigawatts DC to our installed base already of 142 gigawatts as of 2022. Some of the concerns and the issues of the study is essentially, what is all this installed solar do to the local environment? There's been some public pushback on whether or not solar panels actually harm the environment, whether they're a net positive, and various studies regarding such. This study will focus on the urban heat island effect, and whether or not the solar panels cause what's referred to as a photovoltaic heat island effect. This is caused, the urban heat island effect generally is caused by increased development, resulting in warmer temperatures, particularly at night, when the built surfaces in a city, for example, re-radiate heat absorbed throughout the day. And this maintains higher temperatures throughout the entire area. The methodology which I used to produce during the study is indicated by this flow chart. Walking you through it, it starts off with the data, raster files, and then it iterates through the raster files, essentially clipping it to a localized study area about 2,000 meters by 2,000 meters. From there, the digital number values, which are what the raster is originally formatted in, is calculated or scaled up according to band-specific values given by Landsat. And we'll discuss the data source briefly after these pages, but it's scaled up and converted into Celsius for easier interpretation by viewers. Next, so actually the resulting raster there is LST intensity, or just the actual temperature values that are provided by the rasters. From there, I create an index by just taking the minimum value, the maximum value, and what this does is it sets the entire raster on a 1 to 0 scale so that we can compare relative temperature effects across different seasons. After that, I have a transect analysis methodology workflow. What transects are is essentially line profiles that shoot from the edges of the solar array. And what they do is they create a stack profile which samples the temperatures along the line profiles, essentially creating a scattered plot with all the temperature values, and then we can fit a line of best fit or R-squared value to that to understand how temperatures are changing as we move across those lines. It's a bit complicated, but we have pre-construction and post-construction rasters that are further subdivided by winter pre-construction, summer pre-construction, and then same winter post, summer post. These are averaged within themselves, and the output rasters are put into the stack profile tool, which gives that resulting scatter plot. The data used was Landsat's collection 2 analysis ready data, specifically band 10 and 6 of their data was used using Landsat 8's operational land imager and Landsat 7's thematic mapper plus. I chose to use this data as it comes pre-formatted with Landsat's ARD system, the analysis ready data system. And what it is it's a projection that allows for easier temporal analysis by having the same exact extent. And it just facilitates easier analysis. In addition, all of the Landsat 2 collection 2 data represents the highest quality data they can find, already processed for, like solar angle and different things that might affect the image quality. So I just found that easiest to use, and it's very abundant going back to, I believe, the 1990s. The solar sites I used are 3, Red Rock, or the UA Tech Park, which is located in Tucson, Arizona. Red Rock, it's actually called Red Rock, in Red Rock, Arizona, which is this kind of P-shaped one. San Miguel 1 and 2, they're actually 2 solar sites together in Las Vegas, New Mexico, and Jack's Solar Garden in Longmont. I chose these because they represent areas within that receive a lot of solar radiation from, or have a lot of solar radiation available. According to NOAA, they all have an index, I think it's of over 5 kilowatt hours per meter squared per day. One thing to note is that Jack's Solar Garden is an agrivoltaics array showing or having plants underneath the solar panels. And it also differs a little because it's surrounded by farmland as opposed to the 3 others, which are surrounded by native desert scrub and washes. So as a result of the mapping, I was able to produce these. These are the urban heat index maps. Above is the before construction, below is after construction. And what I really want you to take away from these is that on the top row, there's kind of a random distribution of temperatures. And we don't see any clear trends. In the January sections, we see cooler temperatures throughout the scene. And these dotted lines indicate where the solar panel will be built. And in the summer, we see both hotter than normal and cooler than normal temperatures, which is expected because this is just representative of desert scrub right now. There's a persistent wash effect to the right or to the left of this scene, which would be the west. So you can see that in June 16th, 2009, maybe it has creeped into what will be the solar panel extent. And in June 19th, it stays in the west. Post-construction, we see a clear difference. Definitely persistent cooler temperatures relative to the entire scene. And of particular interest on June 11th and June 14th in the southwest side, you can see kind of a cooler temperature band extending about 100 meters into what would be native habitat. The blue or purple dot indicated in this after construction is actually the presence of another solar panel array. And the blue that kind of extends southeast into this scene may be the effects of other construction that's kind of lower in the scene. But yeah, a clear difference. And then I want to calculate this with the transects. So transect analysis shows that before construction, the top two, our R-squared values indicate little correlation between, oh, and I should say that the transects extend north, east, south, and west 150 meters in every direction from the solar panels. Sorry. So the stacked transects show that pre-construction, we see little to no correlation with R values of 0 and 0.02. And then post-construction, we show some correlation, summer 2013, 2014, and then a little bit of correlation winter 2014, but not much. R-squared values indicate the correlation between the X value and the Y value, in this case, distance and temperature. We would expect to see actually that solar panels are heating up the area compared to, or as a result of other studies showing that they might have a heating effect. But in this case, we see kind of a persistent cooler temperatures up until a certain drop-off point, especially when you see the June 11th going into the natural space. The next site, San Miguel, same thing before construction. We have kind of a random distribution of temperatures throughout the whole scene. That's reflected in our transect values you'll see soon. Same thing, transects go north, south, east, west, just at the extent of the solar panels. After construction, we see a significant cooling effect in all of these, but I think one important thing to notice is that in the winter seasons, the effect is kind of blurred into the surrounding areas. And we'll see in the transects analysis and the R-squared values that it results in lower correlation. It's harder to tell how far the solar panels actually are affecting these cooler temperatures and to what extent is it just the natural environment. Especially in January 6th, you can see it blows out to the northwest. But in June 12th, June 7th, we see a fairly restricted heat island effect or cooling effect up to 50 meters. Same thing, we see little to no correlation up at the top, but we have very strong correlation summer 2021 and a little less winter 2021, 2022. Red Rock is another site. This one's in Arizona in Red Rock or kind of Marana area. Again, we see a random distribution of temperatures throughout the scene. And after construction, we see persistent lower temperatures. Essentially the same story. We see that in summer months, it seems more confined. And in winter months, it seems to extend out. Yeah. These are the transects. Unfortunately, I just noticed that pre-construction is on the left side here. Post-construction is on the right side. But again, low values, pre-construction, what we would expect, high values, post-construction. These represent the highest actually, showing really good correlation between distance and temperature. And then the last is a little bit different, Jack Solar Garden. It is the agrivoltaics array, and apologies for the missing data, but what we see here is actually that the pre-construction, we can, and this is verified in the transect, see that it actually has higher and lower temperatures pre-construction within the solar site, and after construction, we kind of see a muddied picture where there's no real correlation between distance and temperature. The only thing to note is that there are persistent cooler temperatures in the area, whereas in the before construction, we actually have hotter than average temperatures. So again, summer 2018, winter 2018-19, we actually see higher R squared values here. And then after construction, we kind of see that muddied effect I'm talking about, lower R squared values, less correlation between distance and temperature from the panels. So yes, in conclusion, I did find unexpectedly, given other studies, that cooler temperatures are near solar panels and they persist within 30 to 150 meters. Across all sites, I saw a more pronounced cooling effect in summer, with cool areas not exceeding 100 meters, and that winter disrupts the pattern, making it hard to assess where the actual solar influence lies. To note that the UA Tech Park in Jack Solar Garden might be, or near urban structures, which might affect the distribution, and it's hard to tell what is influencing what, as in if other buildings are influencing the heat island or cooling effect. And then the Red Rock San Miguel show a more urban to rural divide, more of a natural to urban built up comparison. Finally, considerations. Land surface temperature often overestimates the urban heat island effect. And what I mean by this is that it's hard to conclude exact ground temperatures from satellite data. And in some of the studies I've looked at, there tends to be an overestimation. Like I said, the accuracy of surface temperature products is uncertain because it's just a product of radiance values, and without ground truthing, it's hard to accurately say the exact temperature. So I recommend analysis should just focus on kind of the distribution we see, and we should avoid direct temperature analysis and deriving exact temperature differences from my study. Yes, that is all.